All right, so have you done vectors at all in physics?
No.
Okay. Do you know what a vector is?
No.
I've heard of it. I just
Cool, yeah, that's okay, that's okay. Okay, so that's what we're going to do today. We're going to start from scratch. We're going to start from right at the basics, okay? So this is probably, this unit of vectors across the 4 semesters or 4 units that we do in specialist is probably the biggest. This one and sort of data analysis, right? Calculus, right? But this one we're going to come up, we know now, we do it in unit, we do a bit in unit 2, we do a bit in unit 3, we do a bit in unit 4. So it just keeps building and building and building. So what we're going to do in this unit, and this is why we're doing it now, because we can spend a lot of time on it, is really get that basics down. And once you get the basics on this stuff, it just builds and builds and builds. So it's not too bad. So let's talk about what the heck a vector is. Come here. Okay. So first of all, we need to talk, there's a video there you can watch at your own time. It just goes into some detail, but I'm not going to watch it. This was what I gave it to these guys to do it by themselves. So you've all heard of speed, right? So, not the drone, but the going fast thing, right? Yep. Okay, you're an ice, you prefer ice, isn't it? Speed. Okay, MD, I don't know these ones. I'm way so old. Yeah, I know. It's, yeah. You'll develop your own tick by the end of this 2 years. I can tell you should see these guys when they're on medication.
So what did you take?
Oh, tell me
It's all a blur. Don't remember much.
It's been a long day. It's probably 9 o'clock. So you've heard of speed, right? So can you just tell me what speed is? What is speed a measurement of?
How much accelerator is going?
Well, how fast? Okay. How much do you work?
Did you guys not see the PowerPoint or the presentation?
We saw the presentation. We just didn't see.
See us.
You didn't see you. Yeah. So there was a bit of point. It just
we
said
were meant
principals
to.
address, principals address, principals address.
We actually didn't very well.
Just ask you. You'll tell us how well you did. So, all right. So speed is a measure of how fast you're going. Okay. So technically, it's the distance you've travelled divided by how long it took you to get there. Okay. Now, speed is considered to be a scalar. Okay. So a scalar measurement is it just wants to know how big it is. Okay. Mass, like your mass. So when you get on the scales or don't get on the scales as you see fit, that gives you a value in kilograms. Right. That's a scalar because it doesn't matter which direction you're travelling in, where you are, that mass is your mass is your mass, right? Speed is the same. And there's lots of different values where the value is just worried about the size. Whereas opposed to things like velocity. Have you heard the term velocity? Do you know what it is?
I can't remember.
That's okay. What about acceleration?
See, they also have synonyms.
Isn't that just
yeah.
No, that's speed.
Acceleration velocity.
Okay, so you've heard the words?
Yeah.
Yes. So you've got in the car, right? So any of you driving yet? Richard learners? Okay, so you've got in the car. Cool, that makes things easier. Okay, so you're sitting at the lights, right? Didn't you drive to school this morning? No. Okay, that's good. I'm just wondering, just asking. Okay. No, that's okay. Okay, so you all come in a car?
Yeah.
Yeah, okay, cool. So, got in the car this morning, pulled out of your driveway, drove to school. Okay? So at various points in that trip from your home to here, right, your car went at different speeds. Okay? And as you looked at the speedometer, if you ever bothered to look on the dashboard, right, you'll see that you're going 60, you're going 40, you're going 80, whatever you're doing, right? So that's the speed. That's how fast you're going. Okay? Now, and that's just, and if you look on the speedo, it tells you I'm going 60 kilometres an hour. There's no indication on the speedo that you're going north or you're going positive, negative. It's just a value. That's scale. Okay. Now, if we were able to measure, and you can look at your odometer to do that, you can measure the distance it took you to get to school. Okay. So you can measure that distance, all right, and then you can say, well, it took me 15 minutes to get to school, or it took me 5 minutes, or it took me an hour and a half, whatever. Right. You could then work out how your average speed. Okay, so this distance divided by the time it took gives you an average speed. And most likely, your average will be somewhere between 30 and 50 kilometres an hour. Even though sometimes you're travelling 60, sometimes you're stopped, right, lights and whatever, but the average is that. That's this speed. Okay, now, if you then come home this afternoon, so you jump in the car, follow the same route home, right, assuming the traffic's similar and stuff, it'll probably take you roughly the same amount of time. right? And again, you can work your average speed home. Now, the difference between speed and velocity, right, is that if you travel to school, right, and let's say that your velocity is not the distance you've travelled, but the straight line distance between you and the school and home. So if you're able to get as the crow flies, right, as that's saying, right, and you took that distance, which we call displacement, because displacement is the distance you are from your starting point. Right, so you would have travelled around streets and back and forth and blah, 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 but displacement is the distance you are from the starting point, right, or how far away from the starting point you are, right? Divide that by the time, you'll get a different value. That's your velocity. Now, velocity is also dependent on the direction that you travelled. So if you, let's say your home is here and your school and the school is here, right? So you might have travelled like this to get there. That's your distance, right? Doesn't matter what direction you're in because you're in all sorts of directions. But if you measured the distance that way, straight line, and you could work out using a compass or whatever, the direction, you can measure your velocity. So the difference between speed and velocity is speed just wants a size, velocity needs a direction as well. That's what a vector is. Okay, so a vector is a measurement that requires not just size, but direction. Acceleration is another example of that. Okay, eventually, you won't have done, so you haven't done any velocity stuff in physics yet?
No.
You would have done some in year 10, I know that, but only a little bit, right?
We did like chem with like graphs.
Yeah, okay, so just a little bit, yeah. Oh, right, so you would have looked at the different
Yeah,
graphs and
like
acceleration
A, B.
graphs and so
Oh,
forth?
yeah.
Yeah, that's okay. That's good. That's good. So you would have at some points you had negative gradients and that sort of stuff.
Yeah.
Okay, cool. Okay, so when we look at vectors in, so you can pull yours up and have a look if you want, because it's in one note. It makes it easier, but it's on the screen behind you. All right. So if we start to talk about vectors, we're going to look at not just how far you are from a position, but also what direction you're travelling in. Now, to start with, we're just going to look at positive and negative. Okay, so a positive direction or a negative direction. And we're going to base that on a set of axes, which you're very comfortable with. Right, so we've been working in a Cartesian plane since grade 7 and maybe even before, right, looking at coordinates. So positive x, positive y, we know what they are, all right, and then negative x that way for you guys, right, and negative y. For me, it's the opposite, so when I'm looking at it, that way. Yep, okay, so negative y, okay. And so we're going to look at position. So you can see that on the screen. I'll just turn a little bit so I can see what. Okay. So if we have let's look at these guys here. Okay. So there are a whole heap of examples of vectors. Okay. So they're important because they've got two pieces of information in them. A very obvious starting point, okay, in each of those points, and an arrow indicating the direction they're travelling. Okay. And both of those pieces of information are necessary in order to define a vector. Okay, so if we look at vector from A to B, okay, now we're going to assume that B is the end of the arrow. Okay, now with that A to B, we could identify a location specific for A, a set of coordinates, and we could do the same thing for B. Once we got that, we can then work out, well, how far away is A to B? We can work out the distance, and I'll remind you those formulas when we need to. We don't need them just at this moment, okay? But we did that last year in grade 10. We looked at the distance formula between 2 points. This is going to come up. We looked at gradients of lines. That's going to come up. Right, so all this stuff is nothing new. It's just going to bring it forward into year 11. Woo, okay? So this is why we focused a lot on this last year. We spent a lot of time doing that really basic stuff. And I say really basic in inverted commas, right? Distance between points and gradients, all that sort of stuff. So we're going to come back and haunt you. Okay, so if we look at A to B, now if you look at those diagrams, what can you tell me about A, B and CD?
They're kind of like move.
Yeah, what else? Yep, good, yep, so it's translated, so you want to use the correct that term, but that, what else? So even breaking it down a bit, so not only is it move, what else about it? That you can tell just by looking at it.
Same like Y.
Yeah,
Like,
yeah, possibly, yeah, well also probably, yeah, but what about the length? Just by looking at it, what do you reckon? They're the same, don't they? Yeah, and they are the same. Okay, but without a ruler, you couldn't be 100%. So just maybe on the trust idea. Okay. So if I put my ruler in, all right. So let's. Okay. So we've got. So if I start where the 35 is. wonder if I can move that. No, okay, I don't even know why it's there. Okay, so it's about 10, 11 units long. Okay, so if I then slide that down and move it, also 11 units long. Okay, and you notice it's the same angle, so it assumes it's the same direction. If I move this one down here, then it's 11 units long and so on. So in effect, they're all the same length and all in the same direction. So by definition, they're all equal. Okay, all of those vectors are the same length and in the same direction. And that's how we define a vector, its length and direction. Okay, so AB would be equal to CD, which is equal to OP, which is equal to EF, which is equal to GH. Okay, now if I was playing funny buggers and I decided to go, well, I don't want GH to be the arrow there, I want the arrow there. Are they equal now? Is GH equal to the others now? No, what? Exactly. Right, so as soon as I change the direction, it changes the vector. Even though it's the same length, it's the different direction, therefore you need both magnitude, size, and direction to define a vector.
Are we measuring the direction with bearings again?
We eventually, but not very often, no. So when we get to what are called polar coordinates, okay, you will start with angles.
Okay.
Yes,
Nice.
so we touch on polar and we do a little bit of it, and then we leave it. Mostly Cartesian. Okay, we're mostly going to work in Cartesian. So we're going to define each vector in terms of its Cartesian coordinates, and the way we do that is using Pythagoras' theorem, something you're comfortable with,
I love
right?
that.
Been doing it since grade 8 or something, right? Which is what the distance formula is anyway, Pythagoras' theorem, right? So we're going to be using Pythagoras' theorem and yeah, working out trig. So angle measure from, and it's always measured from the positive x-axis. Okay, and that's just 10. We can do that.
Make me sound a little easy.
Good, that's the idea. I think you get, yeah. Yeah, all right.
Said stuff earlier.
So let's talk about, so we need to work out, well, how do we write vectors down? So there's a number of ways that we can write down a vector. So the first way that we can write them down is to use the points that starting and finishing. So you can see I've got up there, the vector from point A to point B is denoted by AB, so notice they're capitals. Okay, so we use capital letters for the ends, so the points, and you'll notice there's an arrow at the top. So that arrow is pointing from A to B, so that's implying that that's the direction I'm going in. So that's one way we can define a vector, and that's quite a common way. All right. We can also define them in terms of what are called column vectors. Okay, so a column vector is where we, if we knew the coordinates, then we can define that way. So I'll show you what I mean by that in a second. So let's go back to here. All right. So let's pretend for a moment that that's the origin. That's pretty obvious. And let's put in a point here that's 3 units along and 2 units up. Cool. So we know the coordinates of P are 3, 2. So we can define OP, all right? Okay, as, now the reason, so the OP is we need to know its length and its direction, okay? But because it starts at the origin, okay, then OP has a special name, okay, because it starts at the origin. It's called a position vector.
No matter what direction it goes in.
Yeah, no, because it starts at the origin, yeah? So it's called a position vector, okay, because we've got a locked-in spot. Now, if we can identify the position vector, then we can work out its length very, very easily. So what is its length? How would you work it out? Told you I'd bring it up. Pythag, exactly. It's Pythag, right? That's a writing. So, what is it? Just in your heads? What is it going to be? I promise you it's a surd.
Is it root 13?
Right, root?
13.
Root 13?
Was it?
I'm not confirming it.
9 plus 4? Is
Well, it's Pythagoras. It's a squared plus b squared. So what's 9 squared plus 4
You're
squared?
making me dumb.
13. Root 13. So are we cool that it's root 13? Yeah? Okay, now this is not as easy to do in your head. This is where you go, no, what's its angle? So you have to use a calculator for this because I wouldn't have a clue what it is, right? Don't have it here. Fortunately, here's one I prepared earlier.
Thank you.
Okay, so let's This is our first introduction. Have you guys used this in method yet?
Yeah.
Little- Not really. Okay, so I'm just going to pull mine on the screen so that I can guide you through some basics with it, okay? Okay, so let me just pull this out. Okay, so basically there's a couple of things you need to make sure that you're doing before you start. So we're going to go into the run menu so you can just execute straight away, which is the big blue key at the bottom. All right, now because we're going to be working in degrees, okay, in the not too distant future we'll start to introduce different angle types, different ways of measuring angles, okay? But for the moment we're in degrees, which is where you're comfortable, right? So the first thing we need to do is make sure your calculator is in degrees. So it doesn't default to that. So you go Shift and then Menu. So up above the menu you'll see Setup. Let's see, and that screen comes up. Yeah. So a couple of things. Are you input-output mode as math or linear? Math? All that means is that when you put hit the fraction button, it looks like a fraction rather than a little L. You remember your scientific calculators in the old, when you first got them, the little fraction? No? That doesn't know? Okay. Doesn't matter. Don't worry. If it's in math, it'll come up like looking at a fraction.
Yeah.
Okay? Comp mode is what you want. So fraction, you can either... so what that means is fraction result, D over C, means that your answer will always be an improper fraction. So for example, if the answer's 5 on 2, it'll say 5 on 2, it won't say 2.5. If you want it to come up and default to like 2.5, so a mixed number, you can change that. So you can see that there's another option. So if you choose F2, so let's see across the bottom of your screen, you've got little boxes. If they appear, that means that you've got to use a function key, so F1 through to F5, to access those menu options, right? So if you want to choose the mixed number solution, then you choose F2 at changes. And then any fraction problem you do, the answer will be given to you as a mixed number. Now, could I recommend that you don't do that? Okay, all right. I want you to stay working in improper fractions for lots of reasons which will become clear as we start to develop those areas. So I mentioned a moment ago that we're going to be looking at different types of angles. The one that we focus in is what's called a radian, okay? And radians typically are given as improper fractions. So it's just a habit to form, okay? But don't stress about that. You can always convert it if you need to. All right, don't worry about parametric, draw type connect, derivative off at the moment because we don't want to do that. Angle, okay? So you'll see mine's defaulted to degrees. What's yours? Degrees? Rad?
It was rad, now I've changed it to degree.
Good, okay, but this is where you change it. So when we do radians, which is in methods, I think you do it in methods before you do it in specialist from memory, because it'll be in both. So you're also going to find that a lot of the things that we do here, you'll have done already in methods, okay? So you'll get it again, but so that consolidates for you as well. You're going to find that a lot, okay? Which is cool because we get to do it twice, okay? And you get double marks for the same thing. We do take it further, yes, right? But all the basics come from methods. So yeah, so when you come to radians, that's where you change it. But for the moment, we want it in degrees. Then you just hit exit and you're back to your main screen. Okay, so we want to work out the angle, okay, making with the x-axis. So how would you find that?
Like the ratios?
Yeah, so what ratio? What sides do we know for sure? Because we don't trust cadence that root 13 is correct. So what sides do we know for sure?
Sine and cos.
No, sides. What sides do we know?
The opposite and
Adjacent. Yeah, the 3 and the 2, yeah? We know those for sure. They're given to us, all right? The root 13, you know, it's right, okay? No doubting that. But wherever possible, you use the sides, and we talked about this last year a lot, you use the sides that you're given, not the ones you've calculated, where you can, right? So we've got a triangle basically that looks like this, okay? And we know that's 2 and that's 3. And this is the angle I want here. So what ratio is that? 10. Yeah, opposite and adjacent. Yeah, so we know that tan theta is opposite over adjacent. All right, I want theta. So theta is going to be the inverse tan of 2 over 3. Okay, so on your calculator, it's literally what you would have done with your old calculator. So shift, tan, then you bracket, fraction, 2 over. So you can move, so you've got your arrow key, which you're used to from your scientific calculator, so it's not really that different. Excellent equals. So 33.7. Yeah. Just making sure that, yeah. Okay. So I mentioned a little while ago that we can define that OP vector in a number of ways. Okay. The first way, as I mentioned, is what we call a column vector. Okay. So a column vector means it's 3, 2. So I would write it as 3, 2. So that's an example of a column vector. So a column vector is the two coordinates that define its length. So it's always x and then y, and which is what we used to in coordinates. We always do x and then y. So the top is the x, the bottom is the y. It's a column, and it's called a column vector, right? The next topic that we move on to in term unit 2 is something called a matrix, okay, which is more than one column together. So it's tables of numbers, dealing with tables of numbers, and how do we manipulate those. So a vector, a column vector is an example of a matrix. It's a one column, but that's it there. So 3, 2. We're going to look at the other points in a minute. So that's one way to define the vector, OP, is with a column vector. The other way we could do it is by talking about, so we could also say that OP is equal to root 13, 33.7 degrees. Okay, and that's what we call polar form. And I mentioned that, and we're not going to go into much of this detail now. I'm just sort of touching on it, and we'll come back to it later. But basically, that tells me that root 13 is its length, and 33.7 is its angle. And I mentioned it's got to have a length and a direction for a vector. So that's the other way we can define it. Okay? Now, if we look at all these other vectors up here, AB, right? So we've already identified that AB is the same vector as OP, just moved, right? So that would mean that if I was to, and I'm going to have to do this very carefully, so let's say those coordinates are 1, if that's 2, let's say that's 5, okay? And so this would be, so that'd be -1, so that'd be about -2, and I reckon that's about 3. Okay, very carefully chose those coordinates, all right? Hopefully it's obviously y, right? So if I was to define that vector, the starting point is at -2, 3, it finishes at 1, 5. So how far across and how far up? How far across is it? 3. How far up is it? 2. Coincidence? I think not. Right? Obviously, it's not a coincidence, right? So we've got 3, 2, right? So therefore, I can define vector AB as 3, 2. Right? And that's how I define vector AB. Now, it's not starting at the origin, but it's the same length. And if I then worked out its length, 3 and 2, I'd get root 13. If I worked out its angle relative to the x-axis, I'd get 33.7. So even though it's moved and translated, same direction, same size, same vector. Yeah? Now, if we go down to GH, right, which is down the bottom, now I've actually, remember I changed its direction, so it's now HG. That's its direction now. So its length, its length would be the same, but its angle would not be. So if we think about, so we draw in our little axis where we want, okay, so we know that if I was to continue that, that's 33.7 degrees there. All right, so so that would mean that that's 33.7 there from the X rule. Remember the vertically opposite angles back in year 9? So it's been a long time since we touched those, but 33.7, right? So therefore, what would its angle be? Remember, angles are measured from the positive x-axis. So it's that angle there. Alternatively, it could be just, there's two ways you could do it. You could also go that way. So if we follow the grey line, so the positive direction, it would be 180 plus 33.7. Yep, which is? Mm-hmm. 13.7, yeah. And that would be the same, that would be, so you'll see, now if I was to define that vector as a column vector, what would it be? So what would it look like as a column vector? So how far across do I go to go from H to G? How far across do I go? 3, but which direction? Negative, so it'd be -3. And what would be its y value? Or, yeah, -2, because I'm going down. Does that make sense? Yeah? So that would be, so that even though it's got the same numbers, the negative signs imply that, okay, I'm going in a different direction. Yeah? And we get a different angle vector. If I find the length of -3 and -2 vector, when I square -3, I get +9, square -2, I get +4, still get root 13. So I still get the same magnitude, but the direction's very different. Cool? Yep, okay. So this is what we're talking about with vectors, okay? So now, just go back to this idea. What have I got here? Yeah, okay. So this is the different ways we can notate vectors. So I talked about a column. So 2 or 3. Now, 3 numbers just implies a third dimension. So we are focusing purely and only in 2 dimensions in this unit, right? These guys are literally just working in 3 dimensions, the vectors, right? So we don't do that until unit 3. We start to, and we think about the world we live in, we are in a 3-dimensional world. And 4, if you want to start with time, and then if you want to go into this, we're not going to go down that path, are we, boys? Right? We've been down that path a couple of times in our history. So, but we're going to work in 3 dimensions, so X, Y, and Z. All right, but that's unit 3, but that's why it says 3, because you can have a third dimension, right? But we're only focusing 2. I've talked about the AB. Now, the V, so the bold single letter, all right, so I'm going to come back to this idea, where is it up here, right? I'm going to come back to this idea of a position vector, the OP one, right? So if we can identify what our position vector is called, right? So if it's OP, right, because O is the origin and O is always the origin, so never ever use O anywhere but the origin to keep our sanity, basically, right? But then any letter is fine. So this way, if you've got a P. So if I was to define that vector, right, then I would define that, because it's a position vector, I can use the lowercase of the capital letter at the end. So I use the lowercase p to write that. Okay. Now, the little tilde, that's what that little squiggly line is called, the little tilde, denotes it's a vector. Now, the reason I've got bold here, if I can get back to it finally, come on, scroll up. Right? The reason it's bold there is because when you're typing, finding the tilde is a pain in the butt. So you bold it. So, and you can't write in bold unless you scribble, right? We talked about that a couple of times last year as well. We used double lines for real, and that indicates bold. Harder to do with lowercase, right? So therefore, if you're typing, you can use bold to indicate a vector, and then a scalar is just no bold, right? So, or you use a little tilde if you're in here. So when you're handwriting, either with your pen or with your pen, you know what I mean? That pen or normal pen, that pen. You use a little tilde. So every time you denote a vector, lowercase if it's a position vector, 2 capital letters if it's the points at the ends. Okay, so let's have a look. So we've just done things like drawing a line. So, okay, so if I was to ask you to do that question, draw a line segment corresponding to 3, -2, what would that look like? There's multiple possible answers, but what would be the simplest answer to draw for that one?
And the top one's X, right?
Yeah, so if I was to, I'll just put in some axes. I'll make it blank. So what would I do? How would I denote 3, 2? Where would I start? The simplest possible place to start would be where? Origin. Yeah, don't have to, but that would make sense, right? We're going to start here. And what does the 3 minus 2 mean?
3 going in a positive direction and -2 going down.
So 3 out, 2 down. Yep, so I'll go 3 out, I'll go 2 down. Oops, I'm here 2. And I draw a vector. Where does my arrow go? Yeah, down the bottom. Yeah, down this way, yeah? Now, you can put the arrow anywhere along the line. It doesn't have to be at the end, right? But as long as it's showing which direction you're going in. That's it. Literally that simple.
Is
Say
it?
it like that.
But it
It's
is.
gonna
Seriously,
be
is that hard?
No.
No, it's not. Right,
Example 1.
right, let's try this one. There we go. From 2, 6 to 3, 1, so U is a line joining those 2 points. So what's U? So how would you do that? Plot the points, yeah, and connect them. Yep, let's do that. So 2, 6, let's pretend those dots represent that. Let's plot 2, 6. And then you're looking for the trick here, aren't you? You're seriously going, this is way too simple, sir. What are you talking about?
I've trusted you now.
3, 1, okay, so 3, 1, no, wrong colour. So 3, 1 would be sort of around about there.
So accurate, I love it.
Yeah, it's a sketch, who cares? Yeah? So this is 2, 6, this is 3, 1. So I join them up. Right? What direction is my arrow? Pointing up or pointing down? Down, yep. Why?
I was thinking because of the coordinates, the way they
Yeah.
listed.
That's exactly right. Yep, that's exactly right. Again, no tricks. There are no tricks, right? If it says from 26231, that's what it means, right? So we're going from there. So therefore, what is u? So u is that vector. So if I was to define that vector, right, which is called u, right, and it's given as a column vector a and b, what are a and b? So u. So notice I've got it typed in bold, but when I handwrite it, I use a tilde. Yep, cool. So what was u going to be?
1 over -5. Yeah. Yes.
Yes, nodding.
Yeah. I'm just seeing how you guys like so nice.
You good? Yeah,
Yeah.
yeah, that's fine. Yeah, cool. Just because I pause doesn't mean you're wrong. I'm just
Oh, it's
waiting.
scary, okay.
I know, that's the idea.
It's
No.
crushing me.
So that's it. So that's my u value. And I can start any 2 points as long as I go to the right one and down 5. It's the same vector.
That's what the exam's going to look like. Is that question?
Those questions will be, yes. Start with.
I like
It gets a bit more complicated.
Let's do word equations.
Yeah, eventually. Let's go. Let's do so. The last couple of things that we need to be able to do, well, not the last couple of things. That's just defining a vector. That's not very hard. All right. Let's look at some simple examples. So one of the most important things is adding vectors. Okay, and we're going to be doing a fair bit of those. But if we're going to add a vector, I'm going to go away from that diagram just for a moment. All right. So adding vectors simply means it looks like we're doing 2 trips. All right. So if I was to go, let me just put a set of axes down. So wherever we can, we use axes to help us locate. And you can draw a set of axes literally anywhere, right? Yes, you can, as long as they're the same dimensions. As long as they're the same dimensions, you can.
Yeah, but like it keeps giving me syntax.
Then you've got the wrong dimensions.
But the 2x2s. They're all 2x2s. They're not 2x2s.
No, you can subtract. There must be something else wrong. So the syntax is wrong. Are you using the negative sign or the subtraction sign? Try subtraction. Use the actual minus sign. Yeah, see, because how do I know that? Because it said syntax error. If it said mathematical error, then it's like you're trying to do 2 by 2 minus 3 by 1 or something like that, right? Syntax error means you've used the wrong operation. Yeah, that's what it means. So that's why I need to try that first. Yeah, just for future reference. That's all. Okay, so see, easy. Right. Okay, so let's identify 2 vectors. So let's call this dude here. So let's go there, and let's say here is at location 2, 3. I'm just keeping numbers simple to start with. All right. And they'll always stay simple. It's 2 dimensions, for God's sake. Positive and negative numbers. Okay, so let's call that vector u. Okay, now I'm going to put in another vector. Okay, let's do this dude down here, and I'll call that point, again, you love the accuracy, don't you, Cadence? It's annoying me before. Okay, we okay with that? So there, and that's...
Do we write differently if there's 2 position vectors, or do still the lowercase?
Yeah, always. Yeah, always. So as soon as you identify a vector with a single letter, it's always lowercase. You only use the capitals for the points at the end. All right? Pardon me. So, and we'll look at examples of that shortly. If not today, then tomorrow. But, okay, so if I was to add those 2, so what that means is, if I was to travel along, so U has a distance and a direction, all right? V has a distance and a direction. I've just defined them that way. So we know that U is 2, 3. So I'll just write that up here. So U is 2, 3. And V is 3. Whoops, oh, it's not a fraction more. 3, negative 4. Okay, so if I was to travel, so 2, 3, we've already talked about that. It's got a slightly different angle, but it's basically root 13 long, right? And then 3, 4 is 5 units long. 3 squared plus 4 squared is 5 squared. Pythagorean triple. 9 plus 16 is 25.
Oh, a little fast.
Yeah, right. So the first one's root 13, which is what's at about 3.6 or so, right? So let's say it's around about 3 points. Is it? Can you just quickly do it? What's root 13? It shifts. It's above the squared button. Now notice it comes up with root 13. It's real helpful. So above the 8, you'll see S hyphen D.
Yeah.
That's-
Yeah, it's 3.6.
Cool. Okay. So, all right. So this one's, so I'm just using those numbers so we've got a context, right? So this is a roundabout. So this is a roundabout 3.6. It's not exactly, but close enough. Right? And this is a roundabout 5, just so we've got a context in our head to work with. Okay? Now, if I was to walk along U, right, and then I was to walk along V, where would I finish up? Okay, that's the question I'm asking you. So basically, I'm saying to you, well, I want to go along U and then along V. So I'm adding the two vectors. It's like I'm following a orienteering pathway. I go this way, stop, turn, go that way. So effectively, if I walk along U, then I'm walking along to the point 2, 3, right? And then if I add on point V, whoops, brain's working faster than mine. Right, so I do that. If you were to add those together, what do you imagine the answer is going to be? Just, what do you reckon? We've never done this before, so have a guess. What do you reckon it's going to be? Okay, try it. What do you reckon it's going to be? 5, negative 1. Yeah, yeah. So logic would say that, yeah? Okay, so let's do it geometrically. Okay, pardon me. So what I mean by that is, so I've already got U in position. So if I walk along U, it means I've gone 2 units to the right and 3 units up. So I'm now here, right? Now I've got to walk now along vector V, right? So vector V we've defined as 3 units to the right and 4 units down. So if I do that, so 3, this is where my dodgy diagrams come back and bite me in the butt. Okay, so I've got to go for 5. So I've got to go 3 units across there, boom, 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 boom. So 3 units roughly there, right? And I've got to go 4 units down. Okay, so that'd be round about there. Fair enough? Yeah. So, boom, 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 boom. Okay, and I get to there. So what's the coordinates of that point? It's 5, negative 1. Makes sense? And if I draw it in, if I draw that path with the allowances for the freehand drawing, right? It's exactly the same vector, isn't it? All I've literally done is taken vector V and gone slide, which is what we talked about at the start, right? So when we talked about the vectors way up here, yep, here, right? If they're the same direction and the same size, I can literally put them anywhere I want, as long as I keep the length and the direction the same. So all I'm doing in this context, when I'm adding these two vectors, is I'm just taking vector V and go, okay, I'm going to move you over there. That's the same size, same direction. And then I can add them. And therefore, I get a vector where if I wanted to go to just the endpoint rather than going around the outside, I can just go straight there, right? That would be this vector. Ooh, not that vector. Let's try again. That vector there. Okay, and that would be vector U plus V. And that, if I was to define that black line, right, it's 5 units along, 1 unit down. So when I add vectors, all I'm doing is, and we call it the head to tail method. And that's what you see here, right? So if we're adding U and V, right, so we've got to walk along U first. So we go to its head because the arrow is defined to be the head and the starting point is the tail because you're walking in that direction. So your head's that way and your butt's that way, right? So we call it the head and the tail. So the head of the vector is the arrow, the tail is the starting point, right? So we call it the head, the tail. So we're going to go to the head of unit of vector U, and we're going to put the tail of vector V at that point, and then off on V. And then the resultant, right, which is what that vector is called, the resultant vector, is from the starting point to the end point, which is the tail of U and the head of V. Okay? And that's literally that simple. It's literally that simple. Hey?
I'm starting to believe it.
I'm glad to hear it. Okay, so let's look at this example. Yeah, you are. No, you're not. Okay, let's look at this example here, because I'm going to include multiplying by a scalar in just a moment. All right? When we do these examples. Okay? So let's look at U plus V. So if you were to draw U plus V, what would it look like? So if you're going to do your laptop, you're going to do your pen, this to your book. Just curious. Because you might need it. I would like you to try this one. So what would U plus V? So do you want me to send you this page?
I already copied it.
You already copied it over? Except I've added stuff
we
since
move-
yesterday.
Do we move V because it's the second one?
Yes.
Okay.
Yes, that's exactly right. We move V because it's the second vector. So we leave U exactly where it is and we just move V. Do you want to copy it or do you want me to send it? You're just going to copy it? Probably easy. It'd be quicker if you just copy it and just delete the original. We'll get all the notes this time now. It's early. It's annoying.
So Richard is doing an error.
Yeah, so where are you going to put V? No. I don't actually mind the chimes, to be honest with you. It's a bit... I don't mind the chimes, actually. Yeah. Yep, so what would your resultant be?
Oh, like.
No, that's just V. See, that's just V. All you've drawn there, that is just V. So you don't write U plus V there, that's just V. So the resultant would be what? Where'd you start?
Here.
No, you didn't. Where'd you
Oh,
start?
this thing.
There, and where'd you finish? That's it. That's it. Yep. And that would be U plus V. Does that make sense?
Yeah.
Yep. So can I have a look and see?
Well, I was going to do that one.
That's V plus U. Now, in the end, you're going to get the same outcome in this case, right? But we're going to practice the order. So you're going to slide V across, aren't you? Because it says U plus V. So use your starting point. So I'm going to leave U and I'm going to move V over that way. And so it's going to look like that.
If it's negative V, do you just move it in the negative?
No, yeah, that's what we didn't get to. All right. But what do you think? Yeah, so that's that. And so that'll be a U plus V there. What would negative V be? No, oh, it's negative U, sorry. So this is U.
Translate it.
No. Is it the same length? Have I changed the length?
No.
No. So it's going to be the same length, but which direction it's going to be? The exact opposite. So negative V, negative U is that. Well, we're going to talk about that one in more detail tomorrow. We didn't actually go that far. All right, so we're going to look at what happens when this is a negative sign. What the hell? Okay. So, but we'll do that tomorrow. There are some questions to have a play with, which is, this is your Cambridge. I have hopefully got your access to Cambridge fixed. So can you have a look and let me know if that's the case or not? And
That was fine.
it was it you got, but you couldn't get methods?
I got specialist though.
So it's there now? Yeah, good. Because I got that fixed the other day. Yeah, all right. I will see you tomorrow.
Thank you.